Okay, so today we are going to do some new theory, and this is theory we need in order to be able to understand the ideal gas, and it's called the canonical ensemble. So the reason this is useful, well, we've seen that if you can find the entropy of a system, then you can find all of the other thermodynamic properties. So we've seen that the function entropy, which depends upon U and some other properties, X, can be used to find all thermodynamic properties of a system. And in particular, we looked at the case of a paramagnet. Here, X, the entropy depends upon the energy, but it can also depend upon some other things. Like, for example, in a gas, it depends upon the volume of the gas. In a paramagnet, it depends upon the strength of the external magnetic field. So this is X here represents other state properties. Okay? And the two examples which we will use in this is that X equals volume in a gas, or X equals magnetic field H in a paramagnet. So, because I'm going to talk about various different systems throughout the course, X can be anything, okay? If I'm talking about a gas, it can be the volume. If I'm talking about a paramagnet, it can be the field, and so on. But it's other things which determine the entropy. Okay, so that's good. And we've done this for the paramagnet. For the paramagnet, we calculated this function exactly, and we used it to derive the magnetization, the magnetic susceptibility, and so on. But it turns out that this function S is often very difficult to calculate. So for most systems, this function S is too hard to calculate in general, so we need an easier way, and this canonical ensemble is an easier way. So we use the canonical ensemble when it's not easy to calculate the entropy directly from the definition. But it is often hard to calculate the entropy directly from the definition okay, and remember the definition is that entropy is Kb times the log of the number of microstates of the system with these state parameters. So if we find this, then we know everything, but it's often hard to find this, and the canonical ensemble in many cases gives you an easier way. So it's still based upon the fundamental postulate, and it's still based upon Boltzmann's definition of entropy, but it doesn't use it directly. We don't directly calculate the entropy from the definition. So these 3 points just serve to motivate why I'm talking about this thing at all, is to give us a new theoretical way of finding thermodynamic properties. So now let me explain what it is. So we suppose that we connect, as we've done many times before, we connect 2 systems together. So before I've drawn it like this, I put my system 1, connect it to system 2. Connect here means that we allow them to exchange energy. We thermally isolate them from the outside, so they can only exchange energy with each other. Okay, and we suppose that there's total energy is equal to U. Then, we've calculated before the probability distribution, probability that system 1 has energy U1 is, I wrote this formula before, I called it P1 of U1, and it's just, using the third fundamental postulate, it's just given by the numbers of microstates. So in particular, it's the number of microstates with energy U1 of the first system, multiplied by the number of microstates with energy U minus U1 of the second system, divided by the total number of possible microstates of the whole system. So the total number of possible microstates is a sum over U1 prime of the same thing, W1, U1 prime, W2, U minus U1 prime. So this is let me call this equation star. So we derived this equation before, and we're going to use it again here. But in this case, we're going to assume something special about the systems. We're going to assume that the first system is the thing that we want to understand. System 1 is the thing we want to know about. System 2 is a special kind of system called a thermal reservoir, which is a system which maintains a constant temperature. So the temperature of system 2 is independent of heat transfers to and from system 1. So we suppose that the first system is the one we want to study, and the second system here is a thermal reservoir. So these are sometimes called heat reservoirs as well. Okay. Now what this means is that it's independent. The temperature of the system is independent of the energy of the system. The temperature T is independent of energy U2, the energy of the system. This is what we mean theoretically when we talk about a heat reservoir or a thermal reservoir. Even if we transfer more heat to the system or take heat out of the system, its temperature remains constant. Okay, so in reality, there are no systems like this. For real systems, if you give them more energy, you always increase their temperature. But you can imagine a thermal reservoir as being something like an enormous bath of water. Okay? And if I put my small system inside this enormous bath of water, then heat transfers to and from my small system will not affect the temperature of the water very much, because there's a lot of it. Okay? So you can imagine a reservoir as a kind of big body with a very high heat capacity. Right, now we know the definition of temperature in terms of entropy, and this will give us a condition on the entropy and therefore the number of microstates of the second system. Okay, so let's just find out what this means now. We know that if I differentiate ds2 by du2, then this will give me 1 over the temperature, which is a constant. In general, temperature is a function of U. But here it's a constant, which means I can trivially integrate this equation. So I get that the entropy S2 is just equal to U2 over T, plus possibly some constant C. I just integrate the equation. This is a constant, right? So it's trivial. And we know how to relate the entropy to the number of microstates. This is the Boltzmann's formula. Okay? And therefore, we can write the number of microstates in terms of this thing as well. So the number of microstates is the exponential e to the u2 over kBt plus c over kb. So the point of doing this is we've got a formula for the number of microstates of the second system. This is the formula for the probability distribution of the first system. Now, if I assume that this is a reservoir and that these two systems are at thermal equilibrium, then that means that this system is also at temperature T. So by putting this formula here into this equation here, I can determine the probability distribution of energy at temperature T. And this is the point of doing it. W. The equation for W2 into the equation for the probability distribution, which is what I called star down there. Okay, and well, let me just write it out. If you do this, you get the probability distribution of the first system. W1 you still don't know, so that term stays the same. But here I replace this term with an exponential. It's e to the u minus u1 over kBt plus c over kb divided by the sum over u1 prime, w1 u1 prime, e to the u minus u1 prime over kBt plus c over kb. Okay, so it looks rather ugly at the moment, but it does simplify. In particular, you can see that both top and bottom are multiplied by e to the c over kb, here and here, so these terms just cancel. And both top and bottom also have u over kBt and u over kBt, so the u's also cancel. So we get that this is equal to E1 of U1, it's W1 of U1, times e to the minus U1 over kBt divided by this sum. Okay, so this equation is important, and in a moment I'll note some important consequences of it. First, I just want to draw your attention to this thing on the bottom. This thing on the bottom only depends upon the temperature T, right? Because you sum over energies, so it doesn't depend upon energy because you sum over all possible energies. It only depends upon the temperature T. It's a function of T, but this function of T is determined by the microstate distribution of the first system. So this is a function of T only. It doesn't depend on anything else apart from T. But it's determined by the function of microstates. And we've seen that if you know this function, W1 of U1, then you can find the entropy and therefore find all the other thermodynamic properties. So it's possible, and it turns out to be true, that you can also find all thermodynamic properties from this sum as well. So if you know this thing, you can also calculate all the thermodynamic properties. And this is how we simplify, because often you can calculate this without having to know this explicitly. So this function is important, and this is called the canonical partition function. So let me, you can see it right down here, can't you? Okay. This is called the canonical partition function. Okay. And it's usually given the symbol Z. So we call this Z of T. So using this definition of the partition function, I can write the final form for the probability distribution equal to W1 U1 times e to the minus U1 over kBt divided by the canonical partition function Z of T. So now I want to know some things about this formula. The first thing you can see is that the probability distribution, the probability of U1 is directly proportional to the number of microstates which have their energy. And this is a direct consequence of the fundamental postulate. This is the number of microstates. With the energy to U1. That's the definition of W, right? W is number of microstates. It's also proportional to e to the minus U1 over kBt. So this tends to mean that lower energy microstates have a higher probability. If I draw a graph of this, so this is the probability of the microstate as a function of energy. energy of the microstate U1, then it decays exponentially as a function of U. So it decays like this. So this function here is called the Boltzmann factor. And what it means is that higher energy microstates have less probability of being chosen, being realized in this thermal equilibrium. Okay, so it tells you that higher energy microstates are less probable. And in particular, this probability is proportional to e to the minus energy of the microstate divided by the Boltzmann factor. Sorry, they are proportional. Probability is proportional to the Boltzmann factor. Now, this observation relates back to something I asked you a couple of weeks ago on the quiz. On the quiz a couple of weeks ago, I asked you to find what's the difference in energy between the lowest energy microstate, the ground state, and the first excited state. Okay, this was a question on the quiz. The reason this is important is as follows. The lowest energy microstate has a probability somewhere here, right? Now, if the next energy microstate is very close to it, if it's somewhere here, then it has virtually the same probability. So that means at this temperature, there is a good probability of having higher energy microstates occupied. However, if the gap is large enough so that the next energy microstate is over here somewhere, then it has a very low probability of being occupied. Okay? So by comparing this energy gap here, this is delta epsilon, the energy gap between the ground state and the first excited state, by comparing this with Boltzmann constant times temperature, we can see if this state is likely to be occupied. So this question is going to come on the quiz next week. And we can show, for example, using this approach, that at room temperatures, you are very unlikely to excite a vibrational mode in a molecule. Okay? By comparing the energy of a vibrational mode, which we calculated before, to kBt at room temperature. This turns out to be a very small number. Okay, what else? Okay, the final point I want to make is about this canonical partition function z. Z of t is the sum over energies u1 times w1 of u1 times e to the minus u1 over kBt. Well, in this sum, this w1 is just the number of microstates with energy u1, so I can therefore rewrite this as a sum over microstates rather than the sum over energies. So sum over microstates m of simply the Boltzmann factor, e to the minus energy of the microstate divided by kBt. So here I'm using m to denote a microstate, right? Not magnetization, don't be confused. And this is the important form, because this form of the sum, where you sum directly over microstates, is often easier to calculate than calculating the entropy directly. So it can be hard to find this function w, but often it's easier to do this sum directly. Okay, and this is why canonical ensemble is useful. And finally, I've said it in words, but let me write it down. If you know this function z, then you know everything. Okay? You can find all thermodynamic properties. So z of t determines all thermodynamic properties of the system. And this is why it's useful. So it's often easier to calculate z than it is to calculate the entropy directly. And if we know z, then we can find all of the thermodynamic properties. And this is why we use it. So I said I'd give some examples, and I will. So we'll look again, first of all, at the paramagnet example. So I'll show you how you can use this equation to find the properties of the paramagnet, rather than going directly from the numbers of microstates or the entropy. Before I do that, we started this theory part by considering system 1, which is the thing we want to understand, connected to a thermal reservoir system 2. But if you look at these equations, you now see that we've got rid of all of the 2's, right? There's no U2 or W2. So that means in what follows, I will get rid of the units 1 as well. So we're only interested in one system, and I'll just call the energy of that system U, and the number of microstates W, and so on. Okay. But you must always remember that although I write it like this, we're always considering this system in contact with another thermal reservoir at thermal equilibrium. But in what follows, I will forget about the reservoir in that I won't write numbers 1 here. I'll just write U and W. But it means the same thing. Okay. Right, so what kind of thing can we calculate from Z? An example of something we can calculate is the average energy. The average energy of the system, I'll just write like this. The mean, in other words, the mean energy. U. So we've seen the formula for mean energy before. Well, the definition of mean is that it's equal to the sum over all possible values of the energy, of the probability of that value multiplied by the value itself. Okay, this is definition of a mean, right? But now we have a formula for P in terms of the distribution of microstates. If I write this down, this is the sum on U of U. And P of U is W of U times e to the minus U over kBt divided by the sum. Okay, no, let me write it. I'll do it in 2 steps. Divided by the partition function Z. That's just putting in explicitly what is P of U from the formula we'd found before the break. Now if I write this down in terms of, put Z explicitly in terms of the number of microstates using that formula over there, this becomes sum upon U of U, W of U, e to the minus U over kBt divided by Z, which is the sum upon U times W of U times e to the minus U over kBt. So I've just put the explicit formula for Z in there. And you see this is interesting. The top and the bottom look virtually the same in this equation, right? The top and the bottom look virtually the same. The only difference is there's an extra U on the top. There's a U here on the top, which is not on the bottom. So this is not simply identity. But we can write this down simply in terms of the partition function. In particular, this is equal to, I'll explain why in a moment, this is equal to Kb times T squared times the derivative d by dt of the log of this sum. So let me explain why. So this thing I told you is just some function of t, right? So the first fact is, if I differentiate d by dt of the log of some function of t, then this is just equal to, we've done this before actually last week, the derivative of the function divided by the original function. So you see that if I differentiate with respect to t here, I get 1 over this, which gives me exactly what I've got there. And also I get the derivative of f prime, sorry, the derivative of f, what is that? If f of t is some constant, well, constant doesn't matter, e to the minus u over kt, like it is here, then when I differentiate a function like this, I get that f prime of t. I differentiate this with respect to t, that gives me u over kbt squared times e to the minus u over kbt. So you see now that this formula works. I differentiate the log, that gives me 1 over this thing, and that gives me what I've got on the bottom here. Then when I differentiate f, which looks like this, I get u over kbt squared, and here I just want a u, so finally I multiply by kbt squared. So this kbt squared here cancels this u here goes into the sum here, and I get f prime over f, which gives me these two sums here and here. So hopefully you convince yourselves that this formula is correct. And you see that simply this is the partition function. So we get the final result that U, average energy, is equal to KB T squared times the derivative d by dt of the log of the partition function. So this is an example of how we can work out a thermodynamic property, like the energy, from a knowledge of the partition function. And we can again think about the thermodynamic limit. We've calculated the probability distribution, but we expect that in the thermodynamic limit, when the system becomes large, the probability distribution should be sharp, becomes narrow, and therefore this mean is very close to this mean is the most probable and the only probable value of energy U. So we can replace this with a definite value. In the thermodynamic limit, we expect T of U to become narrow. So I can draw these pictures again. In a small system, if I draw P of U as a function of U, it may have some wide distribution like this. It doesn't have to be symmetric. But as the system gets larger, we expect that the distribution should become sharp, like this. So here the average value is somewhere here. But in the large-scale system, the average value is the only likely value. So this means we can treat the average value u as being the definite value u of the system when it's at temperature T. So we can treat u as a definite value in other words, the mean of u is just what is the likely value of the energy of the system at temperature T. So in the thermodynamic limit, we expect that the energy as a function of temperature is given by this derivative of the log of the partition function. So in a moment, we'll do the calculation explicitly for the paramagnet to show you how it works. Before that, I just want to make a note, because we've assumed that the partition function only depends upon temperature, whereas in fact it can depend upon other system properties like the volume and the field and so on. So far we've supposed simply that the entropy and the partition function and so on is only a function of the energy, where it can be a function of the other state properties. So if the number of microstates u, w, is a function not only of u, but of also some other state properties x, as I said, it can be volume or magnetic field or particle number, whatever, then this partition function z is also dependent upon these state parameters. Okay? Function of temperature of the reservoir, and these state parameters. And in this case, we have to replace this full derivative with the partial derivative. U is equal to kb T squared times the partial derivative with respect to temperature, keeping the other things constant. This, and in the thermodynamic limit, this gives you a function of energy as a function of temperature and the other state properties. So nothing particularly complicated, but if there are other variables which affect the number of microstates, then they also affect the canonical partition function like this, and the energy as a function of temperature like this. So now let me show you how it works for the paramagnet. Okay. So the formula is Z is a function of T, and in this case it also depends upon field H, and it's defined as the sum over microstates M. Okay, here M is a very bad choice because M is also like, okay, so let me call microstates mu of e to the minus energy of the microstate, which also depends upon the field in this case, divided by the Boltzmann factor kBt. Okay. Mu is also a bad choice because mu is the magnetic moment, isn't it? What's another letter? K is bad. This is a problem, you tend to run out of letters. Okay, let me call it microstates eta. I'm pretty sure we haven't used eta before. There we go. Okay, so eta labels the microstates, H labels the field. So here, for the paramagnet, eta is the microstate. This is telling you the spin of the direction of every spin in the system. So it's a vector S1, S2, S3 up to Sn, where Si, I've said it before, can take possible values plus or minus 1, which corresponds to spin up, spin down. Okay. So the microstate eta is a vector of n numbers where each number is plus or minus 1. And the energy, U, eta, and H, is, well, each spin has an energy equal to minus mu H times the SI. So the total energy is the sum, I goes from 1 to n, minus mu H times SI. So now I can put these two things into this formula here. So we get that the partition function Z. First of all, the sum over microstates is the sum over all possible values of S, I, and each SI can take plus or minus 1. So this becomes a sum S1, Sn, take values plus or minus 1. So we have to sum over. So really this is n sums, right? Sum S1, sum S2, sum Sn. Okay? And the energy is there, so the minuses cancel, and I just get mu H times the sum. I goes from 1 to n, Si divided by kBt. And this is something which we can calculate, because you see, in the equation here, we've got a sum in the exponential. And whenever you have a sum in the exponential, you can use the relationship that the sum in the exponential, e to the a plus b, is just the product of exponentials e to the a times e to the b. Right? So I can split this sum into a product of exponentials, and this allows me to write it as n separate sums. So S1 goes from plus or minus 1, and the term which depends upon S1 is just e to the mu h S1 over kBt. That's the term which depends upon S1. Then I've got, when I equals 2, I get the sum S2 plus or minus 1, e to the mu h times S2 over kBt. And this goes all the way up to n. So the last term is the sum Sn plus or minus 1 times e to the mu h Sn over kBt. Okay, so this step often confuses people for some reason. So what I've done is, this is a sum in the exponential, right? So here is S1 plus S2 plus S3 and so on. I can use this relationship to write it as a product of exponentials, and then each exponential only depends upon one of the s's, so I can separate the sums into n terms like this. This is now a huge simplification, and this is the reason, well, the main reason why the canonical partition function is often easy to calculate. This has now split the sum into n identical sums. This sum here is the same as this sum here, is the same as this sum here. So all of the sums look the same. This is related to the fact that there are no interactions between the spins. So I can write this as a single sum, S equals plus or minus 1 times e to the mu h s over kBt to the power n. And now finally I can just do this sum. There's only two terms in it, so s is plus 1 or s is minus 1. So this is, when s is 1, I get mu h over kBt. When s is minus 1, I get minus mu h over kBt. And all of this goes to the power n. And following on from what I said last time about triggered hyperbolic functions, this is the hyperbolic cosh function. So we can summarize this calculation. We can summarize this calculation by saying that the partition function for the paramagnet is 2 hyperbolic cosine of mu h over kBt to the power n. So that may seem slightly complicated, but you should compare this calculation we've just done, the calculation of z, t and h, to the calculation we did before where we found the entropy as a function of u and h. So this is the calculation we did last week. This is the calculation we've done now. Look back in your notes and compare them, and you'll see that this one is easier. This calculation I managed to do in, two whiteboards. Whereas this one, because I had to do the Stirling approximation and so on, this one took about 4 or 5 whiteboards for me to write. So in general, this is easier to calculate than this. Okay? So we found it, let's use it to calculate the average energy then. And check that it agrees with what we found before. So the energy U, T and H is kB T squared d by dt at constant h of the log of z. That's the formula we just worked out before the break. Oh no, just after the break, sorry. Now in this case z looks like this. The n, when I take a log, the n just comes down to the front. So this is equal to n kb t squared times d by dt of the log cosh. And the 2 is a constant, right? Log 2 is a constant, so that also disappears. Mu h over kbt. And now it's just a matter of doing the calculus. So when you differentiate log, I get 1 over cosh times the derivative of cosh, and the derivative of cosh is hyperbolic sine, sinh. So this gives you n kbt times hyperbolic sine mu h over kbt divided by hyperbolic cosine mu h over kbt times the derivative of this thing in here with respect to temperature, and it's like 1 over temperature, so that gives you minus 1 over temperature squared, so I get minus mu h over kb t squared. Again, this is the final answer. Sine over cos is tan. So hyperbolic sine over hyperbolic cos is hyperbolic tan. So, and you see that kbt on the bottom cancels with kbt on the top. Sorry, there's a t squared here. ut squared on the top, so that all cancels. So I'm left with u is minus n times mu times h from here, mu, h, and n. And then sine over cos is tan, so I get hyperbolic tangent of mu h over kbt. And you can look back in your notes and you'll find that indeed this is the same as we calculated before. So when we calculated it directly from the entropy, we get exactly the same answer as we calculated now using the canonical partition function. And this shows you that the two approaches are equivalent. Right? I can use the function of entropy, this one, to find this result, or I can use the partition function to find the same result.